presentation. He said, my name is Pedro. I am a PhD student at the Purdue University, and Aniket Kate continue being my supervisor today. Here I'm talking today about Whisper, a distributed architecture for enforcing privacy in credit networks. Most of you already know what's a credit network, but let me also repeat it for some people who doesn't know, so make sure that everybody's on the same page. We know that the credit network can be used to represent trust between users using credit allocations. Let me show you how it works through an example. So imagine that we have two users and they trust each other, Alice and Bob, and assume that Alice has a cat today. And we are gonna call this cat Chloe. Alice goes for vacations and then she asks Bob to take care of Chloe. After she returns, she wants to pay Bob for this service, and then she decides to pay him in CAT, in CAT. In that manner, we have created a new pets currency. We can transport this example into the credit network, creating a directed edge from Alice to Bob with a weight of 20. And as you can imagine, this process can be repeated several times between different users, paying for different services, and a complete credit network can be created. In this work, we focus in the Ripple credit network, and one key point here is that accounts in the Ripple network represent not only users, but also banks like CBW, Cross River in the United States. In Europe, we have the example of Fidor and Santander. Ripple also integrates gateways, or cryptocurrency gateways that allow the use of cryptocurrencies inside the Ripple network. In this manner, Ripple integrates several currencies, in particular fiat currencies like dollars, euros, pounds, also cryptocurrencies like Bitcoin, and even user-defined currencies like dog, cat, pig, or whatnot. Ripple has several advantages over the banking system. In particular, it is possible to perform transactions in a few seconds instead of several days. It is possible to perform intercurrency transactions all over the world, paying a really small fee. And finally, while in the current banking system, transactions are only checked by the banks, in Ripple, transactions are publicly verifiable. At this moment, you might wonder, well, we have already Bitcoin, we have seen already a talk that talks about Bitcoin. Why we need Ripple at all? Well, let's compare them. First of all, they are conceptually different. So Bitcoin is a currency and allow only payments in Bitcoin between the users. In Ripple, instead, it's a transaction network, and as we have seen, it allows to perform transactions in any currency. Moreover, they differ in how the funds are transferred between accounts. So in Bitcoin, it's possible to perform direct transactions between any two wallets. However, in Ripple, in order to perform a transaction, there must exist a path with enough credit from the sender to the receiver. Another difference between the two systems is scalability. So the permissionless nature of Bitcoin makes the whole consensus process really slow, and transactions can be added only at a limited transaction rate. However, in Ripple, transactions have a more local nature, which allows to add transactions faster to the system, and the system becomes more scalable. However, both systems have a common point, and the idea is that transactions are publicly verifiable. In Ripple, this public verifiability is enabled by the fact that they publish the complete list of transactions. They also publish all the links between every two users in the system. Accounts in Ripple are defined by a pseudonym, and as we know already, pseudonymity doesn't really give us privacy at all. And actually, yesterday we saw a really awesome talk in which we saw how to link different wallets and how to anonymize transactions in a Ripple network. In the work that I'm presenting today, we are trying to solve the privacy problem in Ripple. But before I show you how we proceed, let me show you which are the privacy definitions that we are after. First one is transaction value privacy. And we say that a credit network achieves value privacy if the attacker cannot determine the actual value that is transacted, given a fixed sender and a fixed receiver. The other notion that we are after is transaction receiver privacy. And the idea is that the attacker should not be able to determine the actual receiver of the transaction, given a fixed sender and a fixed transaction amount. And as you can imagine, the transaction sender privacy can be defined in a symmetric manner to receiver privacy. In this work, we propose to achieve these privacy definitions via a distributed credit network. So what we propose is now the whole network should not be stored in a single point, but instead, every user should maintain his own credit links. In particular, Alice will locally store her link to Bob, and Bob will do the same. Bob will store his link to Alice, but not only that one, also all the links that he has in the network. Credit network has interesting inherent properties that allow us to go for a distributed credit network. And here are some of these properties. First of all, in a credit network, the credit links of a user determines totally his credit in the complete network. And let me show you an example. So imagine that we have this simple network here. Bob can look at his local links and can determine that his inflow is 450 credits, that his outflow is 40 credits, and obviously his net flow, the difference between the outflow and the inflow, is 410. And the idea is that here Bob can compute locally this information independently of the state of the complete other part of the network. He doesn't need to know what is the state of the rest of the network. The other nice property is now that Bob can check locally that he's not incurring in any credit loss. And in order to do that, what Bob has to check is that his net flow is not changed without his permission. Let's see that through an example again. So imagine that we have the same network as before, and now Charlie wants to pay 5 credit to the bank. In order to do that, Charlie can route the transactions through Bob. And how it works in practice is that Charlie will decrease his credit with Bob, and Bob will decrease his credit with the bank. If you see here, Bob will notice actually that his inflow and his outflow has been decreased by 5, but his net flow is maintained the same. So he hasn't lost any credit in the transaction. Therefore, these properties make credit networks a real target for a distributed system. However, it's not trivial how to do that. So there are some challenges that we need to address in order to create a whole credit network in a distributed manner. Particular, it's not clear. Now we don't have the whole set of links in a single point, so how can we actually find paths between 2 different users in the system? Also, we don't have access to the credit in the path, so how can we actually calculate the credit available in a given path? Moreover, if we are given a bunch of links, how can we ensure that these links are actually conforming a path between 2 users? And we need to solve all these challenges maintaining really strong privacy guarantees. Okay, so as Chloe suggests, let's go one by one over these challenges and see how we propose to solve them. The first one is the routing challenge. And the idea here is how can we determine a credit path from the sender to the receiver? One thing to notice here is that this is not a problem only in credit network, but this is a common problem in many other types of networks, like standard networks, ad hoc networks, or you name it. Existing systems are using what is called the max flow approach. However, we have only inefficient algorithms that solve this issue. They go to cubic in the number of nodes or to quadratic in the number of nodes with a logarithmic factor in the number of links. Alternatively, the llama routing approach has been proposed. The idea is that we don't need all possible paths between 2 users, but we need to calculate only a subset of all possible paths. And it has been shown that this is enough in practice to perform transactions in a credit network, and this approach is more efficient than the max flow approach. And let me show you now an example how this llama routing works. So the idea is that we can have landmarks, and landmarks as highly connected nodes in the network. If we transport this to a current banking system, the banks would be the one that play the role of the landmark. The rest of the users connect to the network via other users in the system. Now what we can do is that we can run a decentralized breadth-first search, starting with the root, starting with the landmark as the root. And every user in the system is going to learn his parent to the landmark. In this example, user 2 will learn that his parent to the landmark is the landmark itself. User 1 will learn that his parent to the landmark is user 2, and the rest of the users, that's basically the same. Now imagine that we want to find a path between user 1 and user 4. What we can do is to reconstruct the partial path from user 1 to the landmark, the partial path from user 4 to the landmark, and then stitch together these partial paths, and we get a whole path from sender to the receiver. Here I have shown only a simple example for one landmark, but if you can imagine, we can have several of these landmarks in such a manner that several paths between 2 users can be reconstructed. Good, so now we know how to get a path, like the one here in the example. The next challenge that we need to solve is how actually we calculate the credit in such a path. The credit on a path is calculated as the minimum credit value available along the path. So for example, in this path here in the figure, the credit on this path will be 10. One way that we can use to calculate the credit in such a path is that every user sends this credit value to the landmark, and then the landmark calculates the minimum on his own. But as you can imagine, this obviously breaks any privacy definition. So what we propose instead is taking advantage of the fact that we are going to have several landmarks. And now a user can create secret shares of the credit link value and send one share to each of the landmarks. And we know that the secret share mechanism, one of the properties of this mechanism is that given only one share of the value, it's not possible to reconstruct the value itself. However, this is not the end of the story. So imagine that the landmark is actually receiving several of these shares. How can the landmark ensure that the share comes from a user that is in the path from the sender to the receiver? In order to solve this, one possibility would be that the users include their identifiers along with the share. In such a manner, the landmark will be able to reconstruct the path. But however, this will again break the privacy of the sender, the receiver, and every user who is in the path. Instead, in order to do that in a privacy-preserving manner, what we propose is the following. So imagine that every two users in the path from the sender to the receiver can create a first pair of signing and verification keys. Now they can use the first signing key to sign the share of the credit value and the verification key of the two endpoints of the link. And now they can send this information to the landmark. And as you can imagine, every pair of links in the path can do the same. What we observe is the following, that this is enough for the landmark to check that this is a correct proof of a path. So imagine that the landmark gets this pair of verification keys. The only thing that the landmark has to check is that consecutive keys in this pair are actually the same. The other point that we observe is that if we make use of first keys for each transaction, any two transactions in the system are going to be unlinkable. So now to wrap up to here, if we put all together, we have a way to calculate credit in a path in a privacy-preserving manner. So what the users will do is that first Bob will create the share of the value, create the first keys and sign this share, and send all this information to each of the landmarks. And as I have said before, every node in the path does exactly the same. Now the landmark has the share of the value of each of the links, so he can use homomorphic properties of the secret sharing mechanism to calculate the share of the minimum value along the path. Once the landmark does that, the landmark can send this share to the sender. And here we can use another property that once the sender receives enough of these shares, he can reconstruct the actual value of the minimum of the path. Okay, so now we have solved the next issue. Now we know how much credit is available in the path. The last one that we want to solve is how actually we carry out the transaction. Now we know how much credit is available. Now we want to use some of that credit to pay from the sender to the receiver. For that, we can use a gossip from neighbor to neighbor. The idea is that the users in the path are going to see anyway the transaction value because their links are going to be locally updated. Therefore, we don't need to hide the transaction value any longer. What we need to do is to assure the transaction is atomic. What I mean by that is that either all the links in the path are updated or any of the links are actually updated. And in order to do that, we perform a two-step transaction. And let me show you that through an example. So imagine that we have a simple network like here, and Bob wants to pay to Alice 5 credit. Bob triggers the payment by decreasing his own link and puts the 5 credit on hold. Now there is an incentive for the bank to forward this credit. The idea is that the bank has received some credit, and now if he doesn't forward this credit, it's easy for Bob to blame him of misbehavior. So assume then that the landmark forward this credit, put the 5 credit on hold, and then Alice can say that he has received the credit. Once he's happy, he sends a message back from the receiver to the sender in order to release all the holds in the path. Here, I have shown a really small example, but as you can imagine, this can be escalated to a longer paths in the network. And in the last 30 seconds that I have, let me show you which is the take-home message from this talk. The idea is that we have seen that credit network has several advantages over the current banking system. However, there are some privacy issues that we need to solve. In this work, we propose the use of a decentralized credit network that achieves privacy guarantees. And we also seen that there are several challenges that we need to address. And in this work, we show how to address the challenge of how to calculate credit on a path, how to check the existence of a path, and finally, how to actually carry out a transaction. And with that, let me thank you for your attention, and I will be happy to take questions. Thank you.